So it's good to have our usual audience and new people who are committed and always open to learn more about renewable energy space and always open for new content and attend our webinars. So while we're waiting for more people to join, because we have quite a lot of people who registered, but I understand that now as we're getting closer to festive season, people are kind of prioritize some other some other engagements. So that's why we are recording this webinar, and it will be shared with everyone who registered but was not able to attend today. Just quick introduction of our company for those who are new and don't know. And who don't know who we are and how we operate. QPQ is investment advisory firm. We have a large pool of investors that we work with, almost 900 qualified investors that invest in solar, wind, hydropower, geothermal, waste to energy, energy storage, hydrogen production, green data centers. Those are the things that we primarily focus on. So we help developers to secure project finance, equity, debt. We also do a lot of M&A transactions. We help pure play developers to sell their projects if that's part of their strategy. We partnered up recently with a green bonds issuing company. So this is something new that we'll be hopefully offering to our clients from next year. And we also are exploring different sources of DevEx, development capital, which is extremely difficult to find in the market. That's why we're also starting our own initiative and creating a fund to support developers in early stages with this last mile funding to bring those projects to ready to build so then we can fund them through our network of project finance type of investors. So we are here to support you guys, support developers with funding, and of course to support investors with project origination. We have an international team of about 35 people, with few more joining from next year, well, next month already in few weeks. I will be posting some links in the chat section where you guys can submit your project if you're developing your own projects, or if you have access to someone else's project. We have a referral program in place that will ensure that you get rewarded for the introductions that you make. Yeah, so apart from this, I'll post a link, my email. If you don't have it, you can send those directly to us. Also a link to referral program and also to our funding accelerator. In the chat, I will be also uploading our speaker's Carlos's presentation. I'll introduce him in a second, that you guys can download. I'll post it in the beginning for those who already joined, and repost it in the end, closer to the end of the presentation, so it's visible for those who joined late. And also for questions, there is a Q&A section where you guys can post questions, and Carlos promised to leave 10-15 minutes in the end to address those questions. So I'd like to introduce and thank Carlos for dedicating time, and it's the second time he's presenting and sharing his wisdom with us. Carlos Birnui Lopez has started his journey in renewable energy in 2005 with his PhD on solid oxide fuel cells. Since then, he dedicated a big portion of his career to advancing renewable hydrogen, tackling climate change through science and engineering. So I will let Carlos to properly introduce himself in more detail and share his knowledge and wisdom about hydrogen. Today's topic is accelerating bankable hydrogen and the role of high efficiency systems in de-risking renewable projects. Very interesting. I really appreciate Carlos joining us. So Carlos, the stage is yours. I'll be on the background managing questions and the rest of communication. I'll be posting a presentation and all other useful links in chat. So please do look, guys, into the chat section so you can share with us some projects, and hopefully we'll be able to work with you. Carlos, the stage is yours.
Thank you, Vlad. Thank you very much. First of all, thank you guys for the invitation. It's a pleasure to talk again in this forum. And as Vlad said, I've been working in green hydrogen for 20 years now. I started in science with a PhD, doing research in solid oxide fuel cells and electrolyzers for more than 10 years until I moved to industry in 2017 to help the products to come to reality and to bring fuel cells and electrolyzers to the market. I was working first in a stainless steel manufacturer. At that time was called Sambic Materials Technology. These days is called Aleima. And since 22, I moved more to the project side of the stories and trying to help the developers to understand a bit better the technology and what they need and what they would be looking after when they are willing to produce renewable hydrogen. So since 22, I'm in Rumble, working in this company. Then I will tell you a little bit more at the end of my presentation. But let me just jump into it and go strictly to business. So I believe you can see my slides, and that's full screen. So yes, as Vlad said, today I am gonna try to talk about how to make the projects more bankable and pitching you into the importance of high efficiency in order to achieve the goals that we need. But I think it is important that we get some background first. I'm gonna tell you a few words about what is governing what we call power tweaks. I guess everyone by this time is familiar with the terminology, but by power tweaks we mean to make renewable hydrogen, green hydrogen most of the time. And that's also one of the topics that I would like to talk. What is considered as renewable hydrogen and what is not, and how much hydrogen we are going to need to actually understand how important this topic will be. But first of all, I think it is also very nice to understand who does what in the Power Tweaks pyramid. This is a representation that I made myself to, first of all, help me to understand who does what in such a complex project as it could be to make ESAF, to make methanol, to make green steel, because you know that green hydrogen project most likely is not only about making hydrogen, is to make something else to bring that product to the industry, most likely to decarbonize that sector. So at Rumble, we've been very aligned with the position or with the view that hydrogen has to be used for those things that are very difficult to electrify. This is very aligned with the hydrogen ladder that Michael Librick has been promoting during these years. So at Rumble, we see ourselves very aligned to all these terminologies, where you would be using hydrogen to those industries where it is very difficult to find an alternative. This is chemicals, fertilizers, but also steel, refineries, and even in the high consuming transportation, high energy intensive transportation, what could be aviation, ferries, well, ships, and even long haul trucks. For and another time, or maybe for later, we will have the rest of the applications on the right side of the screen. Yes, right here. But we are very aligned with Michael in the view that hydrogen has to be for the things that are not possible to do otherwise. However, you have heard that there are many types of hydrogen. We are having the hydrogen that it is currently used by industry, sometimes referred as black, brown, or gray, depending of if it comes from natural gas or from coal. And when it comes to renewable hydrogen, we will be having different types. The most likely to hear are blue and green. but in another countries where nuclear energy is very common, you would hear also the pink one. You will hear even in the later months and years the white hydrogen, what it is called the natural hydrogen. So there is a lot of confusion of what is considered as renewable hydrogen and what is not. And in order to understand what is renewable, what is not, it is good to go to the thresholds that the different regions put, or the different countries put, to label the hydrogen as renewable. You see by these selected regions that I put here in the screen that they vary. When you compare China to the UK, you see double values, one from the other, but you would see that at the end of the day, the values are quite low in kilograms of CO2 per kilograms of hydrogen produced. Because one thing that you need to do is to actually see how much emissions the different type of hydrogen um, type of production will produce. And this is one of the several papers that you can find in literature where nice scientists have done the work of looking at the different manners of producing hydrogen in their whole process, from the very beginning of the extraction of the natural gas to the very end of the production of the hydrogen. In the case, it is gray, blue, turquoise, and for the green hydrogen, they even consider the renewable electricity LCA. So this give us the result that you see here, that it is actually the blue dots, where even when you are with high capture rates, you are not able to commit to these levels. So none of the natural gas related production methods are not giving what we call renewable hydrogen. And this is mainly due to the natural gas extraction. You are already ruining all your thresholds by the way that we are extracting natural gas. Only in the case that you are with very clean natural gases, you could get this number to zero. It is also fair to say that in this study, the SMR is considered the more classical one, and there are new technologies that reduces actually also the gray portion. But it is very interesting to even look at the green hydrogen types, because you would see that in one case, when we are considering only solar and putting the threshold of the UK, we won't qualify. So this means that we need to be very careful of what we are using as renewable hydrogen, because most likely if we are using natural gas, we won't qualify, and if we are using green hydrogen, not we are not having zero as emissions. So that's something important to have in mind. And this is linked to the difficulties that we have on removing the emissions coming from methane, and this is something that we need to address to also attack climate change successfully. All right. So probably after all these years with lot of focus on green hydrogen, that we've been coming to here, because we know that the lower and lower the electricity price gets, we are able to obtain cheaper green hydrogen and therefore competitive. So let me now tell you a little bit more about the quantity of hydrogen that we will be needing, or that we will be expecting to produce in the coming years. It's been a lot of fuss that it didn't help at all, misleading us to believing that we will be needing lots of millions of tons. Here you can see the 2021 scenario from the same consultancy where they were nearly close to 1,500 million tons of hydrogen, now cut to below 400 million tons. So when you go even to people who are much more critical with those volumes, you will be having around 200 million tons of hydrogen that we will be needing. So one of the things that I am always defending, and I'm always trying to convince everyone that at least 100 million tons of renewable hydrogen, in my opinion, green hydrogen, because it is the much more prone to be renewable, it will be needed anyway. And this is a lot of business to make, and this is a lot of this is a great challenge for us to do. And here you can just see the market size of this 100 million tons with a simple calculation, the equivalent electrolyzers that you would be needing for this, and the market size of these electrolyzers. And one of the things that always is been saying about green hydrogen, to sort of attacking it or saying that it is dangerous for the renewable energy um, change, or for the energy transition, is that we will require a lot of renewable energy to make this. Yes, we will be needing lots of terawatts of added renewable energy to produce those 100 million tons, but nothing compared to what it means, because if we use the surface of a small country as Croatia, and this is just an example, I'm not saying that we will do that, right? With solar panels, we will be able to produce the quantity of hydrogen needed, the quantity of electricity needed to produce these 100 million tons. So let's get back to a bit the more into the topic, more into what we've been trying to learn today, and it is to address the problems that we are having with the project, right? And everything starts by understanding who does what, as I told you before. And one of the things that we did at Rumble was studying, yes, before that, because I jumped too early. Uh, One of the things that we need to take into account when we look at the project is our levelized cost of hydrogen. You may hear already what it is, but I wanted to kind of explain you what it is simply. It's just taking all the costs that you will have in your project, capex and opex, divided by the total amount of hydrogen that you will have during the production of during your lifetime of the project. With that, you could actually come with these graphs showing levelized cost of hydrogen versus electricity price. And by playing with the capex and opex of your projects, you will be having different scenarios. We see that we are not facing different the same problematics as we are comparing normally against the gray hydrogen produced in the different regions. In the US, the gray hydrogen is much cheaper because of the cheap natural gas that they have. In Europe, where I am, we are more into the 3 euros per kilo scenario, depending of the price of the natural gas. Now we are in a low price period, so maybe that's a bit lower, maybe between here and here. But as a rule of thumb, I always like to say that we are competing against 3 euros kilo here in Europe, and around 2 euros, 1.5 in the best scenario for US. So we need to understand how we managed to get to this area. We know from the beginning that we need to kind of work with low electricity prices, but we've been learning that it is not so easy to be in this low end of electricity prices, and we will be needing to be stuck with prices more between 40 and 50 euros per kilowatt hour. And we need also to transmit the message that when you are in very high electricity prices, it is very difficult or nearly impossible to produce competitive green hydrogen. So all the parameters need to collide in order to have a competitive project. So one of the things that it has been also very clear is that OPEX plays the more important role in the final LCOH, but one cannot disregard CAPEX either. And this is something that I will tell you in the next slides. But by OPEX, we mean the energy consumption of your electrolyzers, the electricity prices, the lifetime of your stacks, and also the operation and maintenance, depending of what you are having as a project. It could be something that are affecting your final LCOH. By CapEx, we've been starting thinking that it was everything about the electrolyzers. And it is not exactly like that, as I will tell you in a couple of slides. But one thing that you could see in this graph is the impact of the OPEX reduction respect the CapEx. This is just a comparison, reducing the OPEX only 25% versus a reduction of CapEx of 50%. And you see that the LCOH is reduced much more by this smaller OPEX reduction than with the higher CapEx reduction in LCOH. So meaning that if you attack your OPEX problems, you are most likely to have a larger impact in your LCOH reductions. But don't disregard the CapEx. And the CapEx comes into realizing that we are doing much more than buying an electrolyzer. This is an example of e-fuel plant where I try to show the different components or the different parts that would contribute to the capex of a hydrogen plant. So every item would have actually their contribution to the capex. And the electrolyzer, you will see that it is important, but it is not the main driver of the final plant. And this is also taking into account that you buy electricity. One of the problems, or one of the solutions that it's been drawn to kind of cope with the high electricity prices that projects are having is adding your own renewable electricity generation, right? It is a good idea, but it doesn't come without any risk. It comes to adding risk to your project because you would need higher capex and higher things to make, more people to get involved, and so on and so forth, right? And one of the things that it's also important to realize in those projects is that they are rather large, right? So civil infrastructure related costs are also important in the picture. So one of the things that we did a couple of years ago is to dig a bit into this data, and we came with our view on how the capex is built in the different hydrogen projects. We actually put on the table that the electrolyzer systems are much more than just the stacks, right? We thought that the stacks were going to be the higher piece or the higher contribution to the capex in a hydrogen project, because it is where the magic happens, where the reaction is taking place. But there is much more than just the stacks. To start with, in an electrolysis, in an electrolyzer system, You have all the balance of the system equipment, separators, scrubber, purifiers, and also the power electronics related to the stacks. But on top of that, you would have what we call the balance of plant. I like to distinguish balance of plant from balance of the system, because you will need to have the water treatment plant, the extra compressor most likely that you would need for the downstream process, the cooling systems, and the piping and instrumentation controls that you will have in your hydrogen plant. As I was telling you before, the civil works are not trivial here. We are talking about multi-megawatt projects with several buildings to be built from scratch. And this is something that needs to be taken into account and added to the final capex. Most of the cases, we are also dealing with greenfield projects where extra infrastructure needs to be added. For instance, you may need a train track to be constructed, as it is happening here in the project in the north of Sweden for what is called these days Stegra, what it used to be called H2 Green Steel. And this is something that you would need to add to your capex. You may work with the municipality, with the local governments to try to help you to get that infrastructure paid by the state if you want, because it is helping for everyone. But it is there and needs to be paid somehow, right? So when we were digging into the data, what we realized is that the capes were higher than what we found, and most likely was due to the fact that people was disregarding the rest of the equipment that you need in a capes. We're just attending to the electrolysis system and not to the whole hydrogen plant, and even less when you want to do what we call a power to X project, e-fuel, methanol, methane, something like that, right? Steel, fertilizers, So this is something that comes to explain this added capex that we are seeing these days. So I like to challenge the say that we hear so much that the electrolysis system went up in price. No, that's not true. What it went up was our knowledge about the extra equipment that it is needed in hydrogen plants or in power to X projects. And because actually, if you look at the quotes from the different electrolysis systems, I would say most of them have declined with time. They are giving better offers, they are giving better prices, because also more competition is coming and they need to come into this. But a project is much more than an electrolyzer. So this is a bit what you could see on how much the stack contributes to the total capex. This is for a alkaline 1 gigawatt project, very simple the picture, and also how the electrical parts contribute quite a lot. And in here you need to consider that the high voltage transformer is also included when you are connected to the grid. That was what we sometimes found that people were missing. They were thinking that I don't know, someone were going to put it for them because they were going to consume lots of electricity. But well, it depends. If you are going to be a very nice customer, maybe, but you want the electricity quite cheap for your project. So maybe I'm not ready to do that investment myself, and we need to do it in common, or you have to do it yourself to get the project going. So those are the things that we've been learning during these years that we didn't know that were so important and contributing so much to the risk of the projects. Because all this, at the end of the day, what it does, it increases the risk of the projects and open a flag from the equipment. So you see that our data got quite well aligned. What it's been recently shown by the EU data, and in here you see how people are starting also to take into consideration the rest of the utilities. Here we can challenge the other utilities and capex with the alkaline and PEM, but I think the bottom line is that we are starting to understand much better what we need, which level of capex we are starting from, and that would be more this number than rather the other numbers that we were considering when you were looking at these other projects, other data here. You see that some people were reporting even 1,000 euros per kilowatt, and that wasn't actually the case for a total hydrogen project. All right. So to finish my presentation, I want to highlight the importance of the technologies and how we need to actually pay attention to the high efficiency of the technologies and how energy consumption plays an important role to reduce our LCOH. So you know the different types of technologies that we have. We get normally divided in low temperature and high temperature, with much more types in the low temperature part respect to the high temperature. When we go a little bit deeper on understanding the differences of the technologies, you probably already know that the regular alkaline can be either atmospheric or pressurized, but it is made of cheap and abundant materials. While in the case of the proton exchange membrane, is already most likely pressurized, but is using more expensive materials. We have the newcomer in the low temperature wall called the anion exchange membrane, that it is kind of using the advantages of the two walls. So, but at the same time, using a membrane in the electrolyte and cheap and abundant materials as nickel and carbon steel. In the case of the high temperature, what we mean by high temperature is that they operate at temperature above 600. Some people would operate even at temperature as high as 850 degrees C, and they are made of oxides. So actually, this is not exactly correct. So this is actually oxides of these metals and stainless steel. It's a bit shaming that I didn't realize about this before. But here you see the differences that I am telling you in the materials. But one of the things that you notice the most is the difference in efficiency. When you look at the efficiencies in percentage or in kilowatt hour per kilo, it's much lower when we go to the solid oxide. It is something that one thing that one can do is to prognose the stack costs that we will have in 2030, and one could realize that solid oxide are able to compete with the alkaline, and due to the higher efficiency, will have much reduced cost on kilograms per hour. But this is much more put in place when you look at the system level with some assumptions that you can have a look here. I try to put not too low electricity price. So taking into account around 60 euros per megawatt hour, with that percentage of the system of the total capex that I was showing before. 70% capacity factor, assuming that we are having a good hybridization of a few renewable energy sources, and if you allow me, a generous project lifetime. I put conservative degradation times for the stacks, as I believe that most likely, while we will be working with real projects, our degradations will be much higher than we've been seeing in ideal conditions. But I kept kind of the what we've seen, like the alkaline is the more robust by far, decreasing for from giving the less for AM, then PEM, and then the solid oxide. And when you look at this in terms of LCOH, you could see that solid oxide still gives you the best LCOH with values that are not as one would dream. €3 per kilo are still what we've been considering expensive, but this is the numbers that we need to start to get to work, because unless we go below this value that we know that it is not easy to find, or we get even higher efficiencies that solid oxide could get, because you know that solid oxide could get profit of having even higher efficiencies by introducing the excess heat that you have of downstream process. But I try not to kind of put them so much in favor. And but still, you know, it's €3 per kilo what we need to sort of work and realize that we have. So just a couple of slides, a bit more of solid oxides, that you understand why the solid oxides are giving this efficiency, and it is due to thermodynamics. It's thanks to the steam electrolysis reaction can happen at thermoneutral, while the low temperature ones need to push the reaction to higher voltage. So in a solid oxide electrolysis systems, the stacks are working nearly at 100% efficiency. You cap the voltage not to go above that voltage, and you will be having the loss on efficiency for the rest of the equipment around it. One of the things that I also like to highlight about solid oxides is that it's not only an electrolyzer. It is only a platform to do much more than just electrolysis. And it comes here, the fuel cells, and it has even the reversible mode for other applications. This is a picture that I made back in I was 2018, 2019, to try to show the solid oxide cells in all their beauty and versatility. And this is something quite important when you are manufacturing something, right? That you could use it for much more than just one single application, even if the application is very attractive, as I saw by the electrolysis. Other thing that I think it is important to realize about solid oxide is that we have several technologies within solid oxides. We have technologies that work at lower temperature, other ones that work at very high temperature, and technologies that work at intermediate temperatures. And this is due to the different characteristics of the ceramic cell, more precisely by the support that they use. While the metal supported ones are the ones more prone to work at lower temperature, the more traditional electrolyte supported cell will work at higher temperature. It has advantages and disadvantages. Probably the high temperature one is the one that it is being much more used, much robust. What we have much more data to get supported. It also get the profit of using a very nice and abundant material as yttrium doped zirconia, while the low temperature ones would need to use cerium oxide. It could be a bit more rare to find. Although when you look at prices and how they are, the oxides, the metal transition oxides that we are talking in here are not expensive, and they can produce very cheap fuel cells and electrolyzers. One of the important thing to realize also is that between the cells you would be needing a ferritic stainless steel. It doesn't you cannot use any steel, any stainless steel either to the different thermal expansions that you will have with the materials, and at the same time it would need to be coated in order to avoid the different problems that you're having. The more typical is the chromium evaporization that ruins your electrodes very fast. So, but despite what it is believed, there are solutions in the market. Solid oxides has been around for when I started my PhD in 2005. Most of the companies that we see these days out now were already there. Bloom was there, Topsoe was there, Sunfire was there. It's not that Sunfire came a little bit later, but it's not that they have come in the last couple of years. So some of them they have 20 years. Ceres was there. I forgot about Ceres, and they were. It's a technology that has been around for a long time and ready to do the job. All right. As Vlad told me that asked me to leave a few minutes, let me finish with this slide. In my opinion, is one of the most important slides, but I believe it's one of the last ones, and it is explaining us why we need to actually address not only the capex but the opex and the electricity cost, because without putting the three parameters together we won't be able to be on here that we need. So if we will be having very high electricity cost, or very high capex, or very high opex, this won't happen. So we need to actually work in reducing our electricity costs, in reducing our capex, and in reducing our opex. And you see how the opex actually makes a large difference. So I'm not saying that you need to address one thing before the other, but don't disregard one or the other, because then you will have the problem rather sooner than later. So that's a bit the message that I want to send. And also, please, we need to also realize that this is a renewable energy technology, and we need to start small to become large. We need to realize that to do those plus 100 megawatt projects is difficult. It is not easy. And where we are putting our projects is also important because of the abundancy or not of renewable electricity that will allow us to get cheaper prices or not. So think on location, think on your capex, think on your opex, but also try to start small to become large. Not saying that you shouldn't think on becoming large, but try to think in modular solution, trying to go little by little, because your projects will become much more competitive faster in time. All right, that was it. I think I showed you that clean hydrogen is for those things difficult to electrify. that green hydrogen is the best solution to get renewable hydrogen. That LCOH comes when we have lower electricity price, but also higher efficiencies. And I hope that I show you that solid oxide electrolyzers are here to show solutions. And I would urge you to pay more attention to them, to support the companies doing these technologies, and to invest on them if you can. So thanks a lot. Thank you for your attention.
Thank you, Carlos. I love your style. I love the way you present. When I listen to you, the content is, of a top level, but also, the way you present it simply and really, easy to understand makes me, basically reinforces my belief in the future of hydrogen. Because nowadays, experts they split, into, as you well know, some people say it's not possible, the infrastructure is not ready, and then the others who really believe like yourself, and I think I'm on the believer side that considering all the constraints with grid and the challenges with current renewable energy projects, I think hydrogen in general, not only green hydrogen but hydrogen in general, has place to be in the future, and we should embrace it in the way that you described, step by step, focusing perhaps on smaller steps to start with, build up the infrastructure, focus on modular technologies, and eventually it will evolve, like everything else. 15, 20, maybe 25 years ago, some of the current renewable energy technologies were, also people were skeptical about it. Look at where we now, big portion of energy split is now in many countries belongs to renewable energy, and hopefully to hydrogen soon as well. I really appreciate you sharing your knowledge with us. Always very interesting. We have a number of questions, and I appreciate you leaving some time to go over those. So first question is from Kristina Kasyanova. In which country in Europe, according to your information, the price of green hydrogen is $3 per kg? I think there is some misunderstanding here, because I think you referred to just general gray hydrogen when you were quoting this price, correct?
Sure, but I think when you have the right conditions to produce the green hydrogen, €3 kilo could be already found in the EU. In fact, some of the projects that got funding in the hydrogen bank are claiming that they can produce hydrogen at those prices. Those are projects located where the cheapest renewable electricity is these days, that it is Iberia and Scandinavia mainly. So when you are on those locations, and I guess you are also combining it with good designing of the projects, of the plans, and using high efficient technologies, you are not far from there. €60 per megawatt hour is something that I show possible to get there. So if you are in €40 per megawatt hour, it's something that you could be having in Scandinavia. They are on those levels already.
Makes perfect
Many years
sense.
ago.
I suppose you're referring to hydropower in Scandinavia and abundance of solar in Iberia in Spain, right?
Yeah,
And
and
I
wind
mean,
also.
Spain is now, during peak hours, your electricity prices are very low. So perhaps if you manage to run, I don't know if it would work, but just an
Yeah.
assumption, if you
I mean,
use the
the
grid.
main the main challenge that the Spanish projects are having is actually the extra cost that the electricity comes. Many of them thought that they could be having very good prices by connecting to the grid or by getting a PPA, but the extra charges that you get in Spain due to the grid tariffs and all these extra costs that you are having, it's much higher than the ones that they are having here in Scandinavia. But projects who are managed to diminish those risks and to have their own electricity production most likely will be closer to this threshold if they are also taking into account that are using high efficient technologies. Why not? I'm not completely I don't think it is completely impossible that a project in the late decade start to produce at 3 euros kilo. That it is, I think, what it is claiming
Yeah.
in 28, 29, something like that. Yeah.
Mhm. Perfect. Next question from Eric Cooper. Carlos, are you seeing any developments in white hydrogen that are promising? How successful is Coloma at this point?
Well, white hydrogen to me it is very unknown. I must to acknowledge. I am skeptical because I am still mm, puzzled by the fact that we were having so much hydrogen around, available, cheap, and we didn't care to use it for so long time. The people working on white hydrogen, they tell that it is because we weren't looking for it, or we didn't realize until now that could happen. I can't believe that. Why not? But I think one of the importance to me to see in the white hydrogen is the cost related to bring it to where.
Transportation, yeah.
Yeah, because okay, if we may see white hydrogen projects to produce ISAF there, where the deposit of white hydrogen is. It may be feasible and nice if the rest of the circumstances matches. You have logistics kind of easy, you have the CO2 around, So it is not only about hydrogen. That's also one of the things that we've been realizing,
Mhm.
that it is very important to produce cheap hydrogen. It is key, but sometimes without the rest around, you are a bit lost in your or your business case doesn't match,
Mhm.
So but I'm gonna give them the benefit of the doubt, because I would like to read and to support them, to be honest. They need the support on the R&D side. I think is where they are these days,
Mhm.
to try to prove that this can be possible. If it is even better for everyone,
Yep.
it will be amazing. Yeah.
Perfect. All right, another question from Christina. What in your opinion is an optimal share of PEM and SOEC electrolyzers in green ammonia projects?
Look, I don't think it is a question of having a share of technologies. Is having the technology that matches the circumstances of your project. For an ammonia project, the maximum, I mean, I would be proud to go full with solid oxides because of the utilization of the excess heat and the extra efficiency that you would gain from that process. But you may have some circumstances where you have a good PEM technology giving you a very nice prices and performance with your electricity profile that you are having, and assuring and having a much better degradation profile than at the end of the day give you better. So it's case by case. I think it is not, we cannot generalize like that, because we will be having false expectations to people. So think case by case and understand very well your circumstances, because projects are very different one from the other. Yeah.
Perfect. Well, I'm sure you will love next question. It's very technical.
All right.
From Matthias Regraph. In your LCOH projections for 2030, you predict a significantly lower system capex for SOEC than for PEM. This is currently not the case. How do you see the road to decrease SOEC capex, especially since BOP components are very expensive at HT and SOEC have low current densities, leading to a large footprint and increased costs for civil works. Yeah, I suppose.
Yeah, yeah. Um, I believe that we are able to produce the stacks very cheaply. And I believe also that decreasing the temperature of utilization of operation of our solid oxides to allow us to decrease the balance of plant cost. At the same time, the modularization of the different solutions that they are coming now in the market should allow us to decrease those costs. I think in my system, I'm still sharing, no?
Mm-hmm.
In here, I prognose a system cost higher than alkaline. And my assumption here is because the stack cost, unless in PEM, unless large developments will come in the load of the platinum and iridium, then I believe people are working. But for now, I'm not aware of any large developments from an OEM. There is large R&D work going on, but I haven't had any PEM manufacturer tell me I am able to do that
Mm-hmm.
in 2030. And then I put because this and this. Um, I will be very very happy to have them. But I know the solid oxide technology very well. What it is made of, it is what I show you. It's stainless steel metal oxides, and you can get even rid of cobalt by the use of other metal oxides. So the potential to decrease the cost is huge. In case of the PEM, some titanium, some platinum, some iridium is still needed. I think alkaline has lots of potentials also to get down, but PEM needs to work in other directions that could be increasing current density and having larger outputs
Yeah.
per footprint.
Well,
Sorry.
that's what means being an expert. No way I would be able to answer this. So next question is from Sanjay. What is the stack replacement range in years for mature SOEC stacks?
Well, in there, I am assuming also those stack costs that I prognose here. So I would think that once that we've been installing several systems, our stack cost should decrease very very fast,
Mhm.
and those are the ones that we will replace, while the rest most likely we will last probably yeah, I don't know how much, around 10 years, I guess.
Mhm.
I was going to say the whole project lifetime, but most likely not, but much more than the stack. So that also a factor that plays in favor of solid oxide, and also for alkaline, and that's why I believe PEM needs to show that this could be shown by a low use of expensive materials here, because once that it is solved, and I'm sure they will find a way, because this will push everyone to
Mhm.
it's like it's been happening with electrical vehicles. It has pushed everyone to improve, because no one wants to be behind this multi-billion market. So
Mhm.
so it will come. So yeah.
Definitely makes sense. Well, we have a few more questions, so if you don't mind, we'll quickly answer
No, yes,
those.
we can go ahead.
For those who are still hanging out, I think most of the people who joined from the beginning, they're still here. So let's just normally we finish at the end of the hour, but let's take another few minutes to answer questions that we still have remaining. So, from LT Scott, given that many hydrogen projects are currently stalled due to cost, infrastructure, and bankability challenges, do you see ammonia as a more viable alternative fuel for long-haul transport? How do you weigh its advantages against its technical safety and emissions drawbacks compared to hydrogen?
Mm, for long haul applications, I believe that we are going to use for long time still fossil fuels, and then ESAF most likely will be the much more use. ammonia will come for fertilizers, will come for producing for the food requirements that our planet will be needed. And once we will be having much more pressure on natural gas, that it will come sooner or later, because all the studies has shown that we cannot stand this high level of utilization of natural gas that we are having, and even less the higher projections that we see of more using natural gas. It will put pressure on the ones who uses the most natural gas, and it will come there. So that's my view. I could be wrong in here.
Thank you. I really appreciate you sharing your opinion. One more question, and we'll let you go, right? So from Walter, in Italy, electricity price, it's over 100 euros per megawatt hour. That would mean that producing green hydrogen by electrolyzers will be definitely economically not sustainable. Do you agree with this?
Well, I would say that those values are electricity prices, taking all in all. But if you would install renewable electricity generation, this should allow
Specifically,
you to.
specifically for the running electrolyzer, for example, outside of the grid, right?
Yeah, I guess that the solution would be to have your own
Mhm.
renewable electricity generation that would allow you to have less electricity price, but you will be adding risks to your project because your capex will increase. You have more things to take care, and it will be more difficult. Of course,
Yeah.
that's not
I, No, makes
allowed.
sense. I think a lot of projects could benefit from, off-grid solutions. So where there are places where
Sure,
it's difficult to connect and, there is no capacity. So then you can, leverage this and redirect your electricity production for hydrogen, for example. Perfect.
sure.
Well, once again, thank you very much for your time and sharing your knowledge, expertise, wisdom with us. Always great to see you and have you, with our audience. I just want to quickly remind guys who are still here that you can download Carlos's presentation from chats. There are some useful links that you want to, you could explore. If you have projects that require funding, please remember that we help developers to secure funding, project finance, equity, debt, selling projects. And there are also links to our referral programs. If you don't have your own projects, you can share, you can refer others and we'll find a way how we can make it attractive for you. So for those who missed part of the presentation, I'll be sharing recording and along with Carlos's presentation. So thanks again, everyone. Thank you, Carlos, and have a great rest of
Thank
the day.
you.
And Merry Christmas and happy upcoming New Year.
Same to everyone.
Cheers.
Take care. Bye bye.